He kōna ipurangi tēnei nā te reo irirangi o Aotearoa.
Welcome to Elemental, a journey through the chemical elements marking 150 years since the periodic table was invented. I'm Alison Ballance, a rather chemistry illiterate science radio producer from RNZ.
And I'm Allan Blackman, a hopefully chemically literate professor at the Auckland University of Technology.
God, I'm hoping you are too. Now, this journey through the periodic table is going to start from the beginning, but of the alphabet, not the beginning of the table. So we're going to be a bit all over the place. And what are we doing first, and what are its vital statistics, Alan?
Okay, first element alphabetically is actinium. It's got a symbol AC, atomic number of 89, which then puts it down towards the bottom of the periodic table.
I've never actually heard of it, but I gather that this is going to be a story of an element that actually owes its existence to other elements.
Yes, indeed. It's to do with the fact that this element is a radioactive element, and so it's being continually formed and it continually disappears at the same time.
Ooh, I look forward to hearing more about that. So actinium, that's a bit of a strange name. How did it get its name, and what does it mean?
So like many elements on the periodic table, it derives from Greek, and this is the Greek word actus, which means a beam or a ray.
And when was it discovered?
This was 1899, and it was discovered by a French guy by the name of André-Louis Debienne.
Ah, très bien.
And he was lucky enough to be a co-worker of two very, very famous chemists, Pierre and Marie Curie. And they were famous for isolating two elements that we're going to be talking about later on, polonium and radium. They sifted through a ton of a material called pitchblende, and from that they isolated milligrams of both polonium and radium. Debienne did a very similar thing. He used the same material, the pitchblende, and went through the whole rigmarole himself. And from that, he ended up, again, isolating milligrams of this new element, which was called actinium, for the fact that it gave off rays and was radioactive.
So this idea that it's being formed and continually disappearing, tell me a bit more about that. You know, what sort of time frame is that happening over?
In order to understand this, we need to introduce a couple of concepts. Firstly, a thing called half-life. Then,
what's a half-life then?
The time that it takes for half of a radioactive sample to disappear. And then in the next half-life, another half of the remainder will disappear, etc., 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 until after around about 10 or so half-lives, pretty much all of the particular radioactive sample will have disappeared. So some elements have very, very long half-lives, things like uranium, millions of years. Some elements have very, very short half-lives of literally seconds or even parts of seconds. Actinium is sort of what we would call a short half-life. The longest-lived isotope of actinium has got a half-life of 21 years.
What's an isotope?
Isotopes are atoms that have got the same number of protons in their nucleus, but different numbers of neutrons in their nucleus.
So they're like different flavours of it?
Yeah, indeed. Yeah, you may have heard of radioactive dating, for example, which we will talk about. That involves an isotope of carbon-14, which has got two more neutrons in the nucleus than the normal carbon-12 isotope.
Now, I'm just wondering, if we've got something that's constantly disappearing over 21 years, then there's only half as much, and then there's half as much again. So that's that disappearing act of it. Does this mean that it actually isn't very common?
Yes, it does. It is formed from the decay of heavier elements, so either uranium or thorium, and those elements are relatively long-lived. They've got very long half-lives. They undergo decay very, very slowly, and then they form actinium, and then actinium decays very, very quickly. That means that in terms of its overall abundance on planet Earth, it's around about 5 or 6 by 10 to the minus 10 parts per million, which is an absolutely tiny, tiny, tiny amount.
So does it have any practical uses for us at all?
Well, the fact that all of its isotopes are radioactive really does limit its use. However, it has got potential for use in cancer therapy. If we can target that radioactivity perhaps to cancerous human cells or to tumours, then we could use radioactivity for good. We have a branch of medicine called nuclear medicine, which is solely involved with this sort of stuff. And there's one isotope of actinium that has a potential anyway to be used in a thing called targeted alpha particle therapy, or TAT for short. And what they do is to take the radioactive isotope and encapsulate it in a nanoparticle, which, as the name suggests, is really, 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 really small. And this nanoparticle is chemically inert, so it's not harmful to the body. What we then do is take this nanoparticle, implant it maybe in a tumour, and then the radioactivity from the actinium isotope does its trick and hopefully kills the tumour from the inside without getting spread throughout the entire body because it remains contained within the nanoparticle. So that's the whole idea of this, and that is certainly under investigation.
So coming soon to a hospital near us for cancer treatment. Yep. Now, just before we go, what's an interesting fact about actinium?
Okay, if you take actinium and put it in water, the water will glow blue. And this is due to a thing called Cherenkov radiation, which is particles travelling faster than the speed of light.
Wow, thanks Alan. That was Chemistry Professor Allan Blackman from AUT, the Auckland University of Technology.
And you've been listening to episode 1 of Elemental, a journey through the chemical elements.
Elemental is a podcast from RNZ. You can find us at rnz.co.nz/chemistry.
And you can subscribe to the podcast for free at all the usual places: Apple Podcasts, Spotify, Stitcher and Radio Public.
In episode 2 of Elemental, we're going to be looking at aluminium. But until then, it's goodbye from me, Alison Balance.
And goodbye from me, Allan Blackman. Catch you next time.